So in this particular video, we are going to learn about how to perform correlation analysis using statistical software SPSS. And we know that the most commonly used tests are Pearson correlation and Spearman rank correlation. So one is parametric and the other is non-parametric. So as a researcher, you are doing or you are conducting a study, you clearly state that I'm going to do Pearson because you don't know which one you will use for that, and it's always advisable to go with I'm doing Pearson correlation. That's a parametric. When you collect the data and the assumption is not met, you go for the non-parametric. So when you look at your data, it tells you which particular test to use, and that's what we call the assumptions. And I found a particular website, a popularly known website that is offers such good information for you to be able to do the test. So the first thing you need to do is to have your data in SPSS, and the second thing is to compare your findings or your data with the assumptions to see whether you can run the test. So what we need to do first is to locate this particular resource. So it's named statistical lead. So when you have a particular study you want to conduct and you indicated that you are going to do Pearson correlation, since it's the first parametric test or the only parametric test for correlation, you just write Pearson correlation, then you type statistical lead. So when you do that, you just press enter and you have the results. So when you go through here, we have two statistical lead. We have the Pearson product moment correlation, and we also have the Pearson product moment correlation using SPSS. We have another one, you add data, you are going to see data there too. So since we are interested in SPSS, we are just going to click on this. So when you click on this, you are going to be given a brief overview of what Pearson correlation is and also the assumptions and how to perform it. So the Pearson correlation is a measure of the strength and direction of association that exists between two variables that is normally measured on an interval scale or ratio. So it's used to understand whether there's an association between two continuous variables. So let's say for instance you want to find the relationship association between exam performance and the time they spend in revising among students, and with this Pearson correlation is going to help you with that. So you should know that you don't need categorical here and you don't need to code your yes, no, 0, 1 to be able to run this. They must be continuous. Let's say you want to take the BP level, it's not categorical. The first thing you do is to take a continuous variable, that is the figure, and the figure is continuous, and that one will help you. So the variables by nature should be continuous before you can run these tests. So if you look at age, even when you ask somebody what's your age, he's not going to say 25 to 40. He's going to say I'm 21. So by nature, it's continuous. So you now sit down and code them for easy interpretation of your results. So let's go to the assumptions, and we have 4 assumptions. So under the assumptions, when you choose to analyze your data using Pearson correlation, the part you need to spend part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using Pearson. So you need to use this because you should be able to get valid results. But if you don't use these assumptions, you are not going to get valid results. So, and it has 4 assumptions, and your data must pass these 4 assumptions. So if you have one assumption not met, it means that you need to go for non-parametric. You cannot always say that no, since the 3 are met or the 4 are met, the last one, let me ignore it. No. So the first assumption is to ensure that your two variables are measured on an interval or ratio scale. So you make sure that they are continuous, both the first and the second, but you realize that they are not saying dependent and independent, because in correlation you want to find an increase in one. Does it result in a decrease in the other or an increase in the other? We don't have dependent and independent here. Whether you put the dependent first or second, you are still going to get the same results. Coefficient direction will not change. A positive will not change to negative, and a negative won't change to positive. So that's one thing about it. So in my study, I have an example data set here, and you should also know that when you are trying to test assumptions for a particular test, make sure that you have an ID column, and the ID column is here. So this ID column helps you to come in. This ID column helps you to be able to locate outliers should in case you have problems with your data. This can easily be done by importing your data into Excel. Then when you import it into Excel, just create a new column. So it should always be a new variable. So let's say you just create a new column. Let's delete this. So you just click here, right click, new or insert, then you say ID. So you just put 1, 2, 3. So you highlight all, then you double click on this. And when you click on this, this is what you have. So after doing this, you save your data. So when you go through the procedure I give on how to do importation of your data from Excel, you can do it in an easy way. Or better still, if your software is not supported with the automatic recode, you should know that mostly when you have continuous variables, you don't need any recode. Just import it with the Excel and you can go on with the analysis. So you can just close it. So I have my ID here, and I made it ordinal because it's from 1 to the last observation. So I am going to use height and speed. I want to see whether height influencing speed, or an increase in height would result in an increase in speed or a decrease. So these are my two variables, and when you want to know whether they are continuous or not, just go to the variable view. And when you go to the variable view, you see that this height, this weight, in SPSS, anything that is interval or ratio is determined as scale. You won't see continuous variable there. So we have 3 measures: ordinal, nominal, and scale. Ordinal means it has a meaningful rank, with the nominal means it's categorical, and scale means it's continuous. So when you look at here, it's continuous. So when you even import and realize that the measure is, let's say, nominal, you can just change it to scale to ensure that that assumption is met. So since we can see that the first assumption is met, so we need to go to the next assumption. And the assumption says that there should be a linear relationship between your two variables. While there are a number of ways to check, we suggest creating a scatter plot. So you are supposed to use a scatter plot, and it gives you a graphical overview of the relationship between the two variables. So when you have points in this way, like in a straight line, it means that it's linear. When it's moving to the right, it means that it's positive. So the relationship is positive. You still have this line this way, it means that it's negative, and still it's linear. So when you have a line like this or something like this, apart from or either than this, it means that they are not linear, and that assumption is met. It's not met, and since it's not met, you need to stop there and go with the non-parametric. But still, if you realize that your assumption is met, you will need to go to the next assumption. So that's how you do it. It's in an order form. The moment you lose an assumption or you're unable to meet a particular assumption, you can move to the third test. The third one. So you just need to go with the non-parametric. So let's check this by using scatter plot in SPSS. So we just click on graphs, legacy dialogs, scatter or dot. Click on it. By default is checked. You see it's bold, but you can still click on it again and say define. So you put your height here first, put your speed here. As I said earlier, you don't need to do what's the name, whether this is dependent or independent. You just go straight and put any of them in the variables of interest, the boxes you want, and you can run. So you click on OK, and when you do that, you can go to your output. So look at this. Is this linear? How do you know whether it's linear or not? So let's double click this. You see something here, add fit line, add total. Let's add it and see. Is it linear? Linearity. So we close this and we come back. So if you look at this, it doesn't appear to be linear and also appears to be linear. So normally with this, you need to use your own discretion to determine whether it's linear or not. So let's say for instance, this is linear, but this is an outlier and this is an outlier. Let's say we are moving to the next step. There's linearity assumption is met. We just scroll down and move to the third one. There should be no significant outlier. So anything that is further away from the line we draw is an outlier. So it needs to be removed or to check to ensure that whether this is there. So when you remove it, you check the coefficient to see. So we need to check the coefficient for these two to find out whether it influences the scores. And we need to do it this way. We need to go back to our data and utilize our ID that we created. So we come back here again, legacy dialog, scatter dot. Then when we open this, we are going to put the ID, label cases by ID. So we click OK. So when you click OK, you are going to have an output like this. But that depends on the PC or the SPSS version you are using. So when you look at this, you see we don't have cases attached to it like the numbers. So you just double click on this. You're going to see options. Click on options and you see you go to elements, then you see show data label. So when you click on this, this is what you get. So you close this. So after closing this, coming. So let's come back here. We have it here. So you see we have the cases. So when you are able to see the cases and their location. So looking at it, you can see that this is what problematic. This particular respondent is problematic. So that's 128. So we can delete it. So we locate here 128. So this 128. Then we right click. Then we clear. So we look at this one again. Which one is farther away? Let's look at here. Let's clear this. So that's 58. Respondent 58. Then we go to 58 here. Then we clear. So you see that when you are clearing them, this one changes. So sometimes it's confusing. So using the ID, you're able to know those that are missing. Like here, you see, we know that 58 is not there. By here we have 58. By here we have 59. That's why ID use is very important. So let's say we are done with the outliers and we are good to go. So let's go to the next one. But you should also know that should in case maybe you have so many outliers, the moment you delete this, another outlier pops out. Because when you do that, you have to rerun the correlation the scatter plot again to ensure that the outliers are not there. So it doesn't mean that when you just delete, you go through with the analysis. Go back and rerun the test again. That's the scatter plot. When you run it and you still see you delete. So let's say you have deleted up to 5 of them and you realize that you are still seeing the outliers popping out. It means that you have problem with your data. So using the non-parametric would be a safe option for you. So but for this purpose of doing both tests, we just consider saying that this was met. So we go to the next one, which is your variables should be approximately normally distributed. So they consider that you do a bivariate normality, but sometimes it's impossible. So you do the univariate by checking each variable normality, then you can run. So you just come here again with your data, analyze, descriptives. You see explore, click on explore, and you put your variables there. So you can check them concurrently. You don't need to do it separate. Since here dependent list, you just put here, click on plus, uncheck stem and leaf, check histogram and normality plus with test. Then you click OK. So we are going to look at the plus, QQ plus, histogram, and the Shapiro work. So we go down here, look at the first one. So look at here. Kolmogorov-Smirnov is significant. This one is also significant. Partial work here. So you realize that height is normally distributed because when you look at it, you see that it's not significant. It's 0.06 instead of 0.05, even though it's not significant. So it's normally distributed. But when you look at weight, it's not normally distributed. So we scroll down. Let's look at the QQ plus. People, you see, sometimes one thing about research is that, or statistics, is that it depends on the approach. Someone can decide to use QQ plus, someone use histogram. Others will tell you that with the histogram is normally influenced by the sample size. Go with this. So what best suits you? You compare these three tests. Which one is okay? Then you can. So when you look at the height, you realize that it's not significant. The graph looks normally distributed. You see, when you double click this and you try putting a line, let me see. Let's click on this. So you see, they are saying it's normal. So even when you look at the QQ plot, you realize that the lines the points fall straight on the line. So we go down to the second one. You see QQ plots that is trended. So let's check this and you see. You realize that this one is not. So let's double click. Let's add this. Then you see it's not normally distributed. So we can consider looking at the QQ plot too. And no, it's problematic, even though this one looks like a straight line. So since one variable has a normal distribution, we don't need to run Pearson correlation. We need to go with the non-parametric. So whether both are non-normal or one is non-normal, you cannot run the parametric Pearson correlation. You need to run the non-parametric. But for us to be able to understand how to run Pearson and Spearman, we are going to run them both. And you should know that in SPSS, this platform you're using for Pearson is the same platform you're using for the Spearman. And you should also know that again, the moment you have a Pearson correlation, even though your assumption is not significant, let's say, you realize that you cannot run Pearson because the assumptions were not met, and you run it, you are going to find significant results. And finally, significant result doesn't mean that when you run the Spearman run correlation, you are not going to get significant results. The moment you have significant results in the Pearson, you should expect significance in the Spearman run correlation. It's just that the estimates will vary. So the estimates you get from the Spearman when you have a normal distribution is what? Accurate or valid. But if you consider using Pearson, it means that your results or the estimates you are providing is invalid. So we can go with the first Pearson to see whether, even though we don't have a good assumption, we can get significant results. So you just click on analyze, come to correlate, and when you click on correlate, you see bivariate. This partial correlation. So you just leave it, go to bivariate. That's two relationship. Then we put height here. Then we put also speed. So look at here, correlation coefficient is Pearson checked. Others are not checked. So if you check here, you can start to check both or even the three at the same time. So let's say we want to check both. So we just check both here. Then you have to leave it. Any result that is significant will be flagged, so we ignore it this way. Then we click on OK. So we want to see Pearson correlation. What is significant? They will move instead of coming back again. So you click on OK. So if you have your version of SPSS not offering you these two options, you need to check for Pearson and Spearman. You just need to run the Pearson. When you are done, copy the estimate into your Word document, and you can go back and run the Pearson and copy into your Word document again to confirm whether the estimates are similar. So let's look at this. The first thing we get is Pearson height. So this height, this speed. So a correlation of when a variable correlates with itself is 1. So this is invalid. It's not valid. So we ignore this. So we come to this. We look at here. We have some asterisks. It means that the p-value is significant. So when you look at this, 0.002, and we don't see any minus, it's only positive. So it means that an increase in height results in an increase in speed. So the moment you have those who have high height are more likely to have more speed than anybody. So it's like one increase in one variable, or an increase in one variable results in an increase in the other. So it's the same for here. So as I was saying, look at here, even when you compare speed against height, whether left or right, you see we have height here at the left and this at the right, we still the same value. It's the same when you compare speed against height. So it doesn't matter whether you put this variable first or second, you still get the same result. It's significant. So since we have this result significant, we should also expect the Spearman rank correlation result to be significant. So come to this. Look at here, Spearman rank. You see, it's the same thing. Is it not significant? It's significant. Even when you compare it against the opposite, it's still significant. But you realize that the estimates only differ. The non-parametric gives you 0.324 and the parametric gives you what? 0.295. So if you look at this, since you don't have a normal distributed data, it means that you need to go with this. So you just copy it to your Word document this way, and you can report your results. So you can use your APA format or anything. So basically, this is how we perform correlation analysis in SPSS.